So now we're going to talk about the basic buffer. A basic buffer is formed by weak base and it's salt with a strong acid. So first of all, how do it form? Let's say a method is direct. Directly it is given that we have a weak base which is NH4OH. Example, and we have formed with its salt with a strong acid like NH4Cl. B, it is indirect method. Indirect method like HCl is reacting with NH4OH and it is forming NH4Cl plus H2O. And HCl is in limiting reagent. So NH4OH, now it is excessive reagent. Some amount of NH4OH left and some amount of NH4Cl formed. Now indirect method, now if we react NH4Cl with NaOH. Now in NH4Cl, when it is reacting with NaOH, it is forming, it is NaOH limiting reagent, NH4OH plus H2O. So here also we have in this and this in final solution. So these both are called the basic buffer. Whatever we use in the weak part, that is known the buffer. Like here we have used remained the weak base, then it is called the basic buffer. Now let's take an example of calculate the pH of basic buffer. Let's say we have NH4OH which will form NH4 plus OH negative. We have NH4Cl which will form NH4 plus Cl negative. Now Kb we could write for the first equation as NH4OH concentration into OH negative over NH4OH. So here OH negative comes out to be Kb into NH4OH over NH4 plus. It is a base and it is a salt. So POH comes out to be Pkb plus log salt upon base. So this NH4 plus is coming from the salt part. Okay, it's negligible NH4 plus, as we have already seen, common ion effect, and strong electrolyte in presence of weak electrolyte with a common ion. So this is the calculation of POH. Now that is called the Henderson equation. Right, we have seen already in case of acidic buffer. Henderson equation. And it is applicable when the mixture of salt upon base is in the range of 10:1 by 10. Not more than that, then the buffer will not be a buffer. So it is applicable this equation POH when the ratio is like 1 by 10 is to between and 10. So in order to calculate the pH of the solution, we have 0.1 molar NH4OH and we have 0.2 molar of salt NH4 whole twice and so forth. Remember that we get it is 2 NH4 plus, means 0.4 molar of NH4 plus. And it is salt. So what we have, POH equals to Pkb plus log salt upon base. So Kb of ammonium hydroxide is 10 to the power minus 5. So Pkb 5 plus log salt is 0.4 upon base is 0.1. So it is 5.6 and pH comes out to be 8.4. So actually what is the range of, and that is called the buffer range. Buffer range, what is the POH minimum should be of a buffer solution or buffer range, salt upon base. We have seen it is 1 by 10. So POH minimum should be Pkb minus 1, that is, and POH Maximum is salt upon a base equals to 10. So POH maximum equals to pKb plus 1. So what is the best buffer? And best buffer is when concentration of salt upon base is 1. So then POH equals to pKb. So that is the buffer range. So in this problem it is given that we have acetic acid which is 0.1 molar acetic acid, and we are adding 0.1 molar NaOH, and its pKa is given of 4.74. So when acid is 25% neutralized, we have to calculate the pH. Now let's do the calculation. Now all type of pH we have done now. Almost all type of pH we have done. Now this type of question will be given when a good type of question is formed. This type of question, when T equals to 0. If we talk about this container, at T equals to 0 means start. What we have? Acetic acid, which is a weak acid. Now and before equivalence point. What is equivalence point? When all the acid is neutralized by all the base. What we have in the solution? We have acetic acid and CH3COONS, sodium acetate. Now at equivalence point, it is formed a salt. Like we have only salt. So it is a question of salt hydrolysis. Now it is a question of acidic buffer. And after equivalence point, what we have a solution? NaOH, which is a strong base. So acidic base, salt hydrolysis and strong base. So these all the transition through which the solution goes. Now let's say we have initially acid which is 100 mole, and now it has been 20% neutralized or reacted. So it is from 75% acid and 25% neutralized. So we have actually salt which is 25%. Now we can calculate the pH. pKa plus log salt upon acid. Now pKa is 4.74 plus log salt is 25, acid is 75. So it is 4.26. Now at 50% neutralization, when acid and salt and acid both are 50% neutralized, then pH equals to pKa, which is 4.74. And 75% of neutralization, pH equals to pKa plus log or salt upon base. Salt is 75, base is 25. So it is pKa plus 3. pKa plus log 3. And when we have 100% neutralization, the pH comes out to be, it is a question of salt hydrolysis. So pH equals to pKa plus salt hydrolysis, pH equals to 1 by 2. pH equals to 1 by 2 pKw plus pKa plus log C. Now here the problem we have next is calculate the amount of ammonium sulfate. So ammonium sulfate is NH4 whole twice SO4 must be added to 0.2 norm 500 and that ammonia. So ammonia we can write it as NH4OH. So we have asked the amount of ammonium sulfate, mass of ammonium sulfate, and NH4OH we have given. Right. So NH4OH, the information we have given is 500 ml, 0.2 molar. And the solution pH is 9.3 and pKb for NH4OH is, or ammonia is 4.7. So we know pH equals to pH. In case of basic buffer, we calculate POH. pKb plus log salt upon base. So pH is 9.3. So POH must be 4.7. So 4.7 equals to pKb. pKb is also 4.7 plus log salt. Now what is salt? Salt we calculate in terms of the concentration of ammonium ion, and here we get 2C. Concentration is 2C. Right. So 2C, concentration of salt is 2C upon base. Base is 500 into 0.2. So it is actually concentration of base is 0.2. We have already mentioned 0.2. Now here 2C comes out to be 0.2 and C comes out to be 0.1. So what is the mass? We have calculated the C is 0.1. So mass is CMV. C mass is of that NH4 whole twice SO4. Ammonium sulfate is 132 and volume is 1 by 2. So mass comes out to be 66 C. It is 6.6 gram of ammonium sulfate we have to add. Now let's talk about the buffer capacity. Buffer capacity. So what is a buffer capacity? It is denoted by buffer capacity is phi is dx upon dph, where dx is amount of acid or base added and dph is change in pH of the solution. Now let's say we have pH 1. We haven't added any amount of acid or base. A into B divided by A plus B. So this is the formula for the buffer capacity. So now we have given a question. We have to calculate the buffer capacity of the solution and decide which is the best buffer. So A is this acid and sodium acetate. This acid and sodium acetate. So phi 1, buffer capacity of 1 is 2.303 into 0.1 into 0.1 divided by 0.1 plus 0.1, and that is coming down to 0.23230 divided by 2. And buffer 2 is 2.303 is 0.2 into 0.2 over 0.2 plus 0.2. So that is coming on 0.2303. So the buffer capacity of the second one is more. So second will be the best buffer. Now we have a buffer solution where we have ammonium hydroxide, which will and it is a weak base and it's salt with a strong acid. Now if we have add H plus, now if we add OH negative. Now when we add H plus, the H plus will react with OH negative to form the water. So all the H plus will be neutralized. Now if we add OH negative in the solution, so we have excess amount of NH4 plus. So NH4 plus will react with OH negative and it will form NH4OH. And its K is like 1 by KB, and which is very greater than 1. So all the OH minus will absorb and all the OH plus will absorb. That's how the basic buffer works.